So I'm Daniel Krolikowski. I'm a first-year grad student here at UT. I will not be talking to you about the research that I'm doing now, but I will be talking to you about a topic that I worked on for a summer in undergrad and ever since has really stuck with me. One of the big frontiers in astronomy right now is the concept of habitability, right? Whether we're talking about exoplanets or right here in our own solar system, one of the frontiers is what does it mean for a system to be habitable? And can we find this life? And today I'm going to be talking to you about the Saturn system, right here, beautiful picture from the Cassini probe. And I'm going to be talking to you about two moons, mostly one moon, Enceladus, which is orbiting in this diffuse ring here, and briefly mention another moon, Titan, and try to convince you why those are probably the best chances we have at finding a second genesis of life here in our solar system. I know there's a lot of media hype about Europa. Who's heard of Europa, the moon around Jupiter? Okay, who's heard of Enceladus? Fewer, as I was expecting, but I'm hoping by the end of this talk I will convince you why you should put more hype into Enceladus than Europa. And so the first question I want to ask is, why should we even care about Enceladus? It's this tiny moon around Saturn. Why do we care about it? And to do that, I'm going to talk through the history of Enceladus. And so first, it was discovered back in the late 1700s by William Herschel with his 40-foot large telescope. It was the largest telescope at the time. And here are actually his drawings from his original manuscript published in 1790, complete with S's that look like F's. And what he did was he just discovered two new moons. So if you look at the 6 here orbiting just beyond the ring of Saturn, that's Enceladus. Right back then, he was looking through this telescope. All he could really do was discover it. He didn't name it. He didn't really find out anything about it. But that was where the history of Enceladus starts. Now, right, this is the late 1700s. When we think about the solar system, you often think about exploring it with probes or satellites. But of course, we can't do that till the later 20th century. So that gives a whole 2 centuries between its discovery and when we could go explore it physically for scientific discovery. So if we look at the discoveries that were made about Enceladus in that time, we have nothing. Absolutely nothing was found about Enceladus for about 2 centuries, for multiple reasons. One, it's really, really small. So here's Enceladus overlaid with the British Isles. It's about 500 kilometers in diameter. It would fit inside the state of Arizona. So it's really, really small. And if we look at the orbit of some of Saturn's inner moons, here's Enceladus. It's orbiting in this diffuse E-ring, which keep in the back of your mind. But so it's this tiny little thing that's really close to Saturn, which if you've ever looked out at the night sky and seen Saturn, you know is really, really bright. So without a large telescope, or actually going to Saturn and exploring it with a probe, it's really hard to find anything out about Enceladus. All we could see were figure out things about its orbit and see that it's really reflective, which is interesting. So in the early 1980s, the Voyager probes flew past Saturn, and here they were able to finally capture a picture of Enceladus's surface. It might look kind of boring, but it's interesting to note that you have one side that's very cratered, looks really old, and one side that's really, really smooth and looks very young. So there's something going on here that's creating this dichotomy in terrain. And also around this time, people realized a connection with, like I said, it's orbiting inside the E-ring of Saturn, and people realized, wait, it's orbiting in the densest part of the E-ring. So here's this tiny little moon. It's very, very reflective, has part of it that looks very, very young, and it's sitting in the densest part of a ring of Saturn that's just kind of this diffuse reflective material. And so scientists started to put something together. Maybe these are all connected. Maybe Enceladus is actually an active system. It's reflective and sourcing the E-ring, that it's shooting out material, replenishing its surface, and actually creating this ring around Saturn. But of course, you can't figure that out without going there. So in the late 1990s, we launched the Cassini probe, which is still going strong around Saturn, made many, many amazing discoveries. And finally, when it got to Enceladus in 2005, bam, it found what we were looking for. actual geyser plume activity on Enceladus. So here is a picture from 2005 of Enceladus by Cassini. And you can see here it's the south pole of Enceladus, but it's actually has geysers that are shooting out material from its interior, which is absolutely fascinating. And if we look at a more detailed picture of its terrain taken by Cassini, you see even more of a highlight between this terrain dichotomy. You have an old crater, and then again this young, smooth part, and you can even see there are these fissures from which the geysers are actually emitting. When Cassini looks at them, it's really, really hot there. It's active. So something interesting is not only going on outside of Enceladus, but inside. And between the geyser activity and its heat, it was theorized that there must be some sort of subsurface ocean on Enceladus, like Europa around Jupiter or even other moons in the solar system. And sure enough, by looking at how Enceladus wobbles when it orbits around Saturn, Cassini was able to figure out that it wasn't just a regional subsurface ocean, but it has a global ocean. So this is really, really interesting for many reasons. One, the fact that there's a subsurface ocean on a moon that's orbiting around Saturn in the outer solar system, it's pretty cool. But also, we have a south pole where it's a lot hotter. The water is in contact with its core, which means there's probably hydrothermal vents like here on Earth. And this material is exiting Enceladus, meaning that we could fly through it and see what's inside. Now, if we look at this, right, so we have hydrothermal vents, which means there's some sort of energy, there's water there. Sounds like maybe some building blocks of life could be there. And this is where I start to argue that Enceladus is one of the most astrobiologically interesting bodies in our solar system. Not only because it has, water with an energy source, but also because it's emitting that water, meaning we can test and see what's inside. So the second part of my talk is I'm going to be discussing, well, what kind of life could live in the interior of Enceladus, and what exactly would we need to be looking for to detect it? So if we start with the one data point we have for life in the universe here on Earth, right, we can go up the food chain, and does anyone know all the way up, what's the real source of all of life's energy here on Earth? The sun, exactly, yes, right? All of our energy is in some way derived from the sun. And to put it pretty simply, we have a system where we have organisms that use photosynthesis, right? They use sunlight to catalyze a reaction, and they create oxygen. And then there are organisms like us, and our cells respirate. They take that oxygen, and they use it to create energy. Of course, there are some life forms on Earth that don't respirate this way. They use something other than oxygen, but almost all life on Earth works in this very simplified system. Well, that can't work for life on Enceladus, right? We're talking about a subsurface ocean that's trapped beneath a crust of ice. There's no way that sunlight could be providing the energy for this system. So as opposed to our cells, which use oxygen to respirate, there are other things we can use, like hydrogen. So to give a brief schematic of what could be going on underneath the ice crust of Enceladus, so we have the crust of ice, its ocean, and its rocky core. And I said earlier, one of the key things is that its ocean is in contact with the core. And that's because when water reacts with rock, like this, it creates hydrogen. Now, there are organisms here on Earth, like I said, they don't use oxygen, they use hydrogen. And they take hydrogen and they create methane and produce energy that they can use to live. This is a process called methanogenesis, methane creation. And there are communities of bacterial life here on Earth that live this way. And it just so happens that on Enceladus, the same exact thing can happen. So not only are we talking about a system that could host life, we're talking about a system that has a clear analog to life here on Earth, which means it's also easier to figure out what do we need to be looking for to detect this life inside the plume of Enceladus. And I'm going to focus on two key indicators of life in this talk. First has to do with the presence of organic molecules. And by organic molecules, I mean hydrocarbons, so things like methane or ethane that are created out of carbon and hydrogen. Right? You hear organic and you think life, but they don't necessarily have to be created by life. And in particular, we want to look at the pattern with which they would be present in a system. And then also talk about different types of biomolecules, building blocks of life, that could be present in the plume, and what we would need to be looking for to say definitively that their presence means there's life underneath the ice crust of Enceladus. So first, to look at the pattern with which organic molecules could be present, I want to start with just a simple analogy that life is built like Legos. So here I just have a quick sketch of a graph where you have the abundance of something on the y, and then any different type of molecule, right? In this case, we're mostly talking, like I said, hydrocarbons, organic molecules, could be amino acids, building blocks of proteins, our cell membranes, anything like that. They can pretty much all be produced abiotically without life. But if they are, they have an interesting distribution that they're all produced at different abundances, but all of them are going to be there. When it comes to life, however, it's like building with Lego blocks. Life picks and chooses which molecules to use. So if we were able to look not only if these molecules are present in the plume of Enceladus, but how they're present in the plume of Enceladus, we can pick out an abiotic distribution from a biotic distribution and say with more certainty, these things are created from life. Another pattern that we can look at is, like I mentioned, organic molecules, hydrocarbons. There are really simple ones like methane that only have one carbon in them. And then there are really complicated ones that have up to 6, 8, 10 carbons in them. And the amount with which, so here I have number of carbons, you have simple over here and complex over here. If they're produced without life, you have this smooth fall off, right? As you go more complex, they just become less abundant. But if they're produced from life, you have a quick drop off between 1 carbon and 2 carbons, so very, very simple to the next simplest, and then it remains flat. So again, there are certain patterns with which these molecules could be present that if we can find them and look at this pattern, we can definitively say, was it created from life or not? Now, there are also more direct molecules having to do with life that we could detect in Enceladus, that life here on Earth uses to function, and try to say, oh, well, is this also indicative of life? Things like amino acids, right, which are the building blocks of all of the proteins in our body, lipids, which are just fat that make up the cell membranes that make up our body, things like sugars, what we use to create energy in our body. We can look for these things, but just like how the presence of organic molecules wasn't enough, presence of these things also alone isn't enough. We need to know more about their molecular properties. And one in particular that we need to look for is something called chirality. So it basically is just whether a molecule has an orientation or not. So, right, you have 2 hands, right, and they're mirror images of each other, but they can't be superimposed, right? You have a left hand and a right hand. Molecules can also have this property. They can be left-handed or right-handed. And that orientation really makes a difference, right? There are amino acids that if we ingest them and they're left-handed, they might taste sweet, but if we ingest them and they're right-handed, they could either taste salty or kill you, So life is very picky about the certain kinds of chirality it uses, right? For example, here on Earth, all of the amino acids in our body are left-handed, and all of the sugars are right-handed. So if we not only pick out the presence of these molecules, but look to see whether they, pick a certain chirality or not over the other, that could also be indicative of life. So those are some things that we could, look for that indicate life, but how would we find that, right? I mean, it sounds like it's a pretty daunting task, and to put it really simply, just fly through the plume, scoop up some material, taste it, and figure out what's inside, right? It's so easy. It's so easy. But of course, nothing is that easy. And there are different ways we can test material, like the gases and dust and grains in the plume of Enceladus. But I'm going to focus on the most commonly used one briefly, which is mass spectrometry, right? I mean, we've talked about light spectra, right? How different elements have certain fingerprints. Well, you can have that concept for things beyond light. So basically what you do is you have an input material, like the plume of Enceladus. You put it into a box and you bombard it with electrons, right? And then you charge up this material. So then you pass it through an electromagnet, and now that it's charged, it will deflect. The electric fields inside of the electromagnet will make it move, right? And if the molecule is really heavy, it won't move that much. But if it's really light, it'll move a lot. So basically, you get a spectrum of heavy to light molecules, right? And we know how much, nitrogen weighs, and we know how much methane weighs. So we can look for these molecules just by passing the material through a fairly simple system. And the cool thing is that Cassini has done this, right? The orbiter around Saturn has swooped through Enceladus's plume, tasted the material, and figured out roughly what's inside of it. But it's not good enough for life. So here, I have a quick graph. So here, just like before, we have hydrocarbons from simple to complex. There's methanogenic life here on Earth. So we know how much of these things should be produced by life that is methanogenic. And if you combine that with knowing how dense the plume is at different altitudes, you can figure out, oh, well, if you fly over at 50 kilometers, you would expect this much of this molecule. If you fly over at 100, you would expect this much of this molecule. So we can figure out, okay, how much should we expect to see if there's life? Well, Cassini's sensitivity is not particularly good. It's all the way up here, right? It's, almost 100 times worse than what we need. But Cassini was also launched in the 90s, so its technology is pretty old. And with new mass spectrometry, the sensitivity is down here. So any biotically produced molecules we can detect. They're created in very small amounts, but we can detect them now, which is very, very interesting. And not only is our sensitivity better, right? Here, I only have a few molecules, right? As you go more and more complex, they get heavier and heavier and heavier. And your mass spectrometers can only go so heavy. Cassini couldn't go that heavy, but now we can. So we can really push to more complex molecules and test to see whether these distributions of molecules are what we expect for life. So just to quickly wrap up on the key indicators of life that I've mentioned, right? First, we want to look for this pattern of organic molecules that are present in the plume, right? And with new mass spectrometers, we can do that. We can detect life-created molecules if they exist in the plume of Enceladus. I didn't touch too much upon how we would detect these different kinds of biomolecules. The detection methods get pretty complicated, but to broad brush it, there's additional technology you can add to a mass spectrometer to, say, figure out if an amino acid is left-handed or right-handed. So it's pretty phenomenal that detecting life is really, really hard, mostly because we don't know if it's there, but our technology says we can do it, which is very phenomenal and mind-blowing. So I talked about Enceladus and potential life on Enceladus. I also mentioned Titan quickly. What about Titan, right? I'm sure people have heard of Titan. It's the biggest moon of Saturn. It's really, really interesting and also astrobiologically interesting. Right, Titan, it has a really, really thick atmosphere. It has standing bodies of liquid, hydrocarbons, basically lakes of natural gas on it. It has dunes. It has a liquid cycle. Right here we have a water cycle. There they have a methane cycle. Well, let's see, atmosphere, liquid, it kind of sounds like something, kind of sounds like Earth, right? So could Titan also be habitable? Well, it's an interesting question, but really, really complicated. Any life on Titan, on the surface of Titan, would be markedly different than life here on Earth. I absolutely love this picture because you have Titan in the background and Enceladus in the foreground. And like I was saying, life on Enceladus is still water-based. It's like life on Earth. But life on Titan would require a completely different chemistry than anything that we could possibly see here on Earth, meaning that its habitability is in some ways more interesting because it would completely change our definition, but also much, much harder to think about. And so, just to wrap up, I want to put up, I think, the most beautiful picture ever taken This is by Cassini. Saturn's backlit here by the sun, and you can see the E-ring, which Enceladus is right here, right, emitting from its geysers and sourcing the ring. And you can't quite see it on this projector, but right here in the background is a pale blue dot. It's the Earth-Moon system. So finding life beyond the Earth is an extremely daunting and difficult task. But finding a second genesis of life, right, a second time that life has been created, would completely and profoundly change everything we know about the universe. And I hope that I've convinced to you tonight that Saturn, and in particular Enceladus, is the place to look. Thank you very much.
Thank you. It's a Trappist. Okay, so we have some time for some questions. I'll take the one standing right in the back. Yeah.
How collaborative is your team? So you're touching everything from biochemistry to the root of organic chemistry to pretty aggressive physics. How collaborative is that team? Is it founding physicists or?
Yeah, so sorry, the question was how collaborative is the team that's studying this? And mind-blowingly collaborative, right? When I briefly worked on this topic, one of the things that just blew me away was the fact, right, my advisor was a trained astronomer, but he knew everything about chemistry and biology and physics and how they all interplay. He was in contact with other astronomers, geologists, chemists, biologists. It's one of the most interdisciplinary fields, I think, that is being studied today. So it's a very complicated web of people that work on these things.
Anyone up top? No? Right here.
So why do you downplay Europa relative to...
Whoa. So the question was, why do I downplay Europa relative to Enceladus? And one of the reasons is because I worked on Enceladus, not Europa. I will say I'm biased. But really the big reason that I downplay Europa with respect to Enceladus is that Enceladus has these plumes that are nearly continuously erupting. So it's very, very easy to test the material that's inside of Enceladus. Europa, there's some tenuous kind of evidence that there are geyser activities, but nothing continuous and nothing on the scale that Enceladus has. So the main reason I play up Enceladus so much is that we've already tested the material that's being emitted from Enceladus. So it provides a fairly simple way to figure out what's going on inside.
Mostly a matter of access and not necessarily differences in processes that are going on?
Yeah, exactly, right? I mean, it's very possible that, right, the biology that could be going on in the subsurface ocean of Europa would probably be very similar to Enceladus. So astrobiologically, they're the same, but yeah, it's more of an access thing.
Right there? Yeah.
So with regards to like Enceladus and like sub-ocean you were talking about, if mass spectrometry is like really what's been helping us identify that is it actually like water as we know it, like H2O, or is that just the assumption because it's a fluid, so you can only assume, or could it also be there could be other liquid gases that are like possible? Is it just like an assumption that there's like an ocean and then the mantle or whatever like that? Like how are you guys able to actually find like what is out of that fluid because you can't actually get the content itself?
Right. So the question was basically, what's the composition of the subsurface ocean of Enceladus, and do we know for sure that it's water, or are we assuming that? Well, we know for sure it's water, right? When you test the plume, over 90% of the material that you scoop up is water vapor or water ices. So yeah, the ocean is primarily water, right? But it's not like the ocean that you would walk into on, the Gulf Coast or something. It has other things, right? It has methane in it, which could be indicative of life. It has nitrogen in it. We know that it's very salty. It's also very basic, which is interesting because that could mean that there is some biology going on. But So no, it's not quite like an ocean here on Earth, the typical ocean, but no, it is still primarily water.
Okay, last question.
Both the light you mentioned on Titan and that on Enceladus would be primarily carbon-based. How do you know we're looking for carbon-based life forms?
So the question is, how do we know we're looking for carbon-based life forms, right? All life here on Earth is carbon-based. And that's just kind of an assumption, right? I mean, that's one of the issues with the idea of habitability, right? Because the only way we can say something is habitable is basically if life as we know it could live there. So we're just assuming that it would be carbon-based. Yeah. But I mean, I agree, that's an issue, right? I mean, who knows if life could be not based on carbon, but because that's the only life we know, we kind of have to implicitly assume that it's carbon-based.
Okay, great, thanks. It's a TRAPPIST.